see the screen I'm sharing?
Yes.
Okay, great. So, so first of all, thank you for having me today at the seminar. So I'm a PhD student at the University of Science and Technology, HEH, from the Institute of Electronics, and my supervisors are J.Mojsiejuk and Witold Skowronski from that institute as well. So what I want to briefly talk about today is sort of, I want to make an argument, and maybe it's not really an argument because nobody is going to disagree necessarily, that there are some simplifications we can make to certain models, in this case, LG models, and simulations that actually give us really neat results. So this simulation package called CMTJ sort of started as a side project for me when I was a master's student. And it turned out to be quite interesting to see how unexpected results you can get out of it. And of course, the name is a little bit misleading. It suggests magnetic tunnel junction applications, which is true. It was original idea, but eventually this turned out to be just a fraction of what the package can do. So briefly, let me go over the outline of my talk. So I'll briefly just talk about the main features, why we decided to sort of do it that way. I'm going to briefly go over the LG model used in the package, and then we're going to go over the simulation examples. And the simulation examples are going to be specifically referring to experiment behind it, but so keep in mind that all of those results are somehow supported by the experiment, at least qualitatively. So starting first is, why do we need a macrospin model? So CMTJ is a macrospin model package. When I was doing micromagnetic simulations, even at bachelor studies, I have noticed that there's a lot of things that maybe we don't need that much compute for. So basically, we're running very expensive simulations and supercomputer HPCs, and there are a lot of applications, even within the experimental agreement, that we can sort of reduce the overhead of that computation and get away with a simpler model, a lighter weight, at a cost of fast prototyping. So we can do fast prototyping, we can do quick testing, we can play around with different parameters, change things quickly, and then figure out, okay, this is working this way. This is what happens if I change this or that, right? So that was the main sort of idea behind developing this. And the other thing is that with the existing packages, even though they're excellent in what they do, they are not really that well integrated with machine learning packages and the languages we write, usually software analyze our data, whether it's C++, maybe you do root, or Python. Pandas, also root is available for Python. So this mix of things made me think, okay, maybe I can get away with macromagnetism as opposed to micromagnetism. And if so, for what range of applications I can do it. So to sum up what the package is about is here you have the repository, so you can visit and download and play for yourself. There are examples and so on. This is available both in C++ and Python. It uses the macrospin engine simulation, and each time we try to reference experimental techniques to make sure this is actually working as expected. And it has 3 levels of simulation. It has layer, which is just a low level. We'll talk about it later. You can put the multi-layers out of layers and then stack the devices to compose the spintronic circuits out of it. And if you need more speed, although I find it not really necessary recently, you can do easy parallelism with multiprocessing in Python or via threads in C++. So this is just a brief overview. So starting on how this looks in practice, it's like I mentioned, 3 levels of abstraction. You start with a ferromagnetic layer. which is the lowest level you can have. You define your layer, and then you can combine your layers into, in this case, I'm using junctions, but it's generally multi-layer devices. And then what happens, you can have multiple of those devices and join them together into one big system, and then simulate the whole system. So here you have, for example, I firstly define layer, then I define MTJs, 2 of them, and I put the MTJs in the last lines in a stack, which is a series stack connected in series. We'll talk about how it looks experimentally and what we can get out of it as an example. And if you want to define just a single layer, this comes from the Python interface. The previous example was from C++. I'll be mixing Python with C++ during this presentation. So here we have a layer. We define its basic static parameters. And then during the simulation time, we can redefine a dynamic contributions. And what are those contributions? So these come from originally LLG model. And there have been numerous talks during this conference about the LLG related stuff. So I'm not going to be dwelling too much on this, but basically we're using LLGS, Landau-J.Mojsiejuk equation in that form. Of course, you may have seen a different form where you have different constants here, but numerically they're equivalent, and the package supports both of them. And you solve this equation. There's also stochastic version of it that we can solve in the package, but you solve it, and then the way you set up your simulation is through the effective field contributions, right? So you have this decomposition of the effective field, in this case, into 6 elements, which is an isotropy field, interlayer exchange coupling field, dipole field, demagnetization, Ashtot, and external applied magnetic field. And this is all on the layer level, on a single ferromagnetic level. But like I mentioned, you can merge layers and join them into bigger circuits. And when you do that, you enable different types of coupling. So of course you have interlayer dipole coupling, but you can have inter-device layer dipole coupling, as well as the electric coupling. So there are inbuilt models for that as well. I'm going to go briefly over this in the example section. So right, so now we can also control each of the field contributions, right? So we can set any driver. So we can drive our effective field contribution with an arbitrary function, up to you how you decide. Maybe, well, usually you probably want to do some maybe decayed exponential, maybe some pulse step, or a sinusoidal excitation. And you can do it for any field contribution that I've shown before. Even if it's like a vector excitation, you can do it. You can define a vector along 3 axes changing in time. That's also possible. So in this particular case, we can control, this should be without the dot product, sorry, this is an error. We define J constant from interlayer exchange coupling, and then we can set a driver to any of those functions. So that's how you excite your systems on different levels, whether it's layer level, a stack layer level, or junction layer level. And then one interesting question I had when we've been developing this is what we can actually do with this, like practically what sort of experimental techniques we can mimic and support with these types of simulations. Even though they're like relatively simple and maybe to an extent somewhat naive. So what can we do? So here is a listing of basically what we've found so far to be working really nice. So obviously you have RH loops, MH loops, which is resistance field, magnetization field loops. One surprising thing that worked really well is a harmonic Hall detection technique, really popular experimental techniques for spin Hall angle determination. We'll go over it in the examples as well. Ferromagnetic resonance, spin diode, and PIMM, pulse-induced microwave magnetometry, both of those techniques also are very well represented by those models. Electric synchronization of MTJs. So that's also like, inter-device coupling, which is, extremely potentially useful in neuromorphic computing, as well as we can go for spintronic oscillation simulators and probabilistic bits or devices, especially like thin layer nanomagnets, and we can analyze their switching like using the stochastic form of the LHC equation. And obviously you can analyze the magnetization trajectory, which comes as a bonus to all of that. Well, so going over step by step, let me start with the pulse-induced microwave magnetometry. So I sort of wanted to make a juxtaposition of the code with the sort of decomposition of what can happen in the experiment. So firstly, we set up the device, we set up our layers, right? And we join them into a junction or a multi-layer device, and we excite them with a small pulse of Ashted field in a perpendicular direction. And we take a weighted average of the response and then compute f of t. And that's on the left is roughly all the code you need to do that in the package. So for each, you sweep with the field, right? External field, you can sweep, of course, with the angle. You set the external field driver to all the layers in the system. You set the Oersted driver, which is Oersted field driver, which is a step driver with a small value and very short duration. You set it for all layers. And then what you're doing is running a simulation with a reasonable step in simulation time. And then you can compute FFT out of it. And that's how you get this pulse-induced magnetometry output. And those images are what represents the simulation. And in this particular case, what it's sort of trying to visualize here is that you have this secondary branch, that inverted U-shaped branch here and here, which is if you increase the interlayer exchange coupling constant J, specifically, if you increase it, it gets wider. If you decrease it, it gets shorter. In this case, it's antiferromagnetic coupling. Sorry, this should be just as 1.6 minus 4. This is 0.1.6 megajoules per meter squared. So this is actually exactly what we can observe in the experiment. We can see and confirm that this is enough. This macro spin model to observe the quantitative and qualitative effects of the interlayer exchange coupling getting larger and smaller, and thus influencing this inverted U-shaped secondary branch. Another example, as I mentioned, is this electric coupling of MTJs. So on the right, you have a really simple diagram of how you can set it up. So you have a spectrum analyzer, and in this case, 2 MTJs in series. And you're interested in analyzing how the spectrum of this joint system looks like. And it turns out you can take a very simple model, a really simple model of the electric coupling with a single coupling constant G. And the magnetization here comes from the free layer. So in this case could be the top layer of the magnetic tunnel junction, and P is the polarizing or fixed or reference layer, which is the bottom layer in this drawing. If you do this experimentally, then in CMTJ, you just need to define something like this, which is say, okay, in this case, I have a stack composed of 2 magnetic tunnel junctions. I'm going to set my coupling strength, and this is anti-coupling, so a very small value of 0.0.1 in this case, mixing. And then you set the current density driver that's coming through the system. And it turns out like you can also very nicely see that in experiment. This is simulation data. The qualitative same is in experiment. So basically, what it represents, if you scan, if you apply different magnetic fields, external magnetic field values, and you measure the spectrum of the constant current density, for a negative coupling value, you can observe that those two MTJs, which in the absence of coupling, you can see there are two separate lines here. They snap together through quite a range of synchronization period. And if you have coupling, positive coupling constant, they go further apart. So they sort of get pushed away. Of course, the high order secondary harmonics are visible here as well, since it's like a higher contrast. So it sort of shows that, like, with even that simple model, just a little bit of the simulation code, you can basically reproduce this really interesting and potentially useful experimental result. And this was like the most surprising example, which is harmonic Hall detection techniques. I think, so this is basically using the spin-orbit torque formulation with the damping-like and field-like torques, which go into LOG equation. And those are directly computed through those curves. So these curves come from the first harmonic and the second harmonic response of the system, measured in this case in longitudinal, field arrangement. So if you look here, we in the harmonic Hall technique, we are primarily interested in the quadratic region and a low external field regime. So we observe it here, right? And then for second harmonic response, we're interested in the linear region in the slope of the linear region here. And that's the most important thing. And you can see from those images that the agreement with the experiment is really good. So in the simulation code, again, it comes as really simple. We just require the magnetoresistance computation as per this publication from Kim and others. And we just set our excitation of the system. In this case, it's a junction, but it can be single layer. It's a single layer. So you do here a sinusoidal excitation for field-like and damping-like terms, which in here come from or in amperes per meter. And again, you swipe with the field around the simulation, and then you compute voltage spin diode, and then out of the spin diode, you can extract the first and second harmonic response. And that's how you get those simulation results. All right, so to finish up, I also want to tell you that we have a graphical user interface in addition to the simulation package. So you can sort of play around it visually. Of course, it's more limited than the simulation package since, well, it's a graphical user interface, so we could only implement a finite number of ideas. But you can go over the trajectories, you can go over PIMM, you can go over spin diode, FMR. You can also define multilayer devices and scan with field or angle of the field and compare it with the experimental results. So this is, of course, again, open source and available to all. And maybe a quick word on what's potentially a direction of development that we can take. So the first thing is, it turns out like you can make this macro spin assumption, which is sufficient for implementation of dipole interaction-based dipole reservoir computing. So this is something I've been trying to do recently. It turns out you can do it with this microspin package that we developed quite easily. More electric coupling experiments. So this is, again, maybe potentially useful for neuromorphic computing, as I mentioned. Another implication of that stochastic LOG is that obviously we can use this stochasticity, as I mentioned before, for probabilistic computing And then again, we can use this to build arrays of probabilistic bits because we assume this uniformity of the magnetization per a layer or per device. And of course, will be also, if you have any ideas what are applications that might be useful for you and your experimental verification, please let me know. You have my email. And again, you can find the code and the package capacity with the documentation under the link here in this repository. So thank you very much for your attention, and I await your questions if you have any.
Thank you very much. Do you have any questions?
Yeah. Yeah, so thank you for a nice talk. So first question is, what's your final goal? You want to implement very effective classical computing electronics, or you want to implement a quantum computation? What's your final goal? Because probably it was not so clear for me from very beginning.
Yeah, so originally it was to have a highly effective model for experimental verification. Like it turned out that you can actually apply it to neuromorphic computing applications. It's not quantum computing as per se. I don't think that's I don't see it at this point, but for neuromorphic computation, especially for dipole-based and electric-based coupling, so anything you can do computation based on this seems like a very good final goal. So in this case, circuits which can basically utilize dipole for reservoir computing, electric coupling for reservoir computing, as well as some probabilistic computing. It's not quite quantum though. It's a separate.
Okay, so what's the main advantage of your approach in comparison with this classically existing CMOS technology?
Oh, well, so it's, so in this case, like it's purely for now, more like theoretical. So it's not really yet, well, apart from the experimental techniques that we already confirmed, right? So this has like very short-term advantages. But for long-term advantages, right? So we don't know yet how it would fare about against CMOS computational techniques. But for the package itself, it's definitely super quick. So it's like it doesn't really have any sort of, let's say, competition, because there hasn't been a package, say, that focuses on macro spin. There's micromagnetics packages, but there is not really that much in macro spin. So in that regards, I think, there is this niche that this fills out nicely, especially for quick experimentation. And then to make sure that, this works better than existing experimental implementations of this reservoir computing, you have to do actual experiment, right? So not really that much to do with the simulation. You can check your feasibility of computing this in practice, but you won't really, in terms of at least energy efficiency and switching speeds, you probably need to do it experimentally. You have to implement it first.
So I can make you one suggestion. So there is very well developed so-called rapid single quantum flux electronics that is pushing a single quantized magnetic flux. Think about possible creation of interface between rapid single quantum flux electronics. It is very well developed. It has 100,000 Josephson junction on one chip that works in cryogenic condition. Try to integrate this with your kind of concept. So maybe there would be quite important, because since you use micromagnets, that you can try about possible interface and possible something like that. So rapid single quantum flux electronics. So well, you can I can send you some papers. So maybe we can talk if you are interested.
Yes, please. At all means. Yeah, definitely. So what I'm saying, basically, the same interface may apply to different underlying, say, equations, right? It doesn't have to be LG equation specifically that we're solving. The whole interface is sort of an abstraction of it. But in this case, in this talk, we're presenting a specific package. But I'm very curious to see whether we can work something out with this. Thank you for your suggestion.
Okay, thank you. Do you have any other questions or comments? No, thank you. Thank you again.
Thank you.
And now we have the break until 5 p.m. So thank you very much.
Recording stopped.